So now we've come to the point where we're going to introduce the idea of something called the integrated rate law. So we just finished talking about rate laws, and really what the rate law does is tell us what the rate of reaction will be at some concentration. So for example, we had rate laws for first order reactions, right? And for a first order reaction, we would have written reaction rate, right, is equal to, for example, K times A to the first for a first order reaction, right? Because that's what the first order means. It's to the first power. So if you knew this concentration, you could calculate what the reaction rate will be, right? Now, there's something that's called an integrated rate law, which is derived from the rate law. And it's actually more useful in a lot of ways than the rate law. What the integrated rate law does is it tells us what the concentration will be at any time. So let's say you started with 0.1 molar of a reactant and you knew the rate law, you could actually calculate what the concentration would be a minute later or 2 minutes later or 3 minutes later, things like that. And so it actually turns out to be a very useful way of analyzing data. So the reason the terms are similar is because integration is a mathematical tool, basically, that we use in the sciences for converting a lot of things, in this case, rate law data, into time data or time equations. And so it's just a technique, okay? Now, you may not have learned it yet, but it doesn't really matter because all we need to do is know what the equations look like and how to use them. And the equations are given to you on tests, or they're also, you can find them in a nice table at the back of your book. So again, rate laws tell us concentration rates at a given concentration, but integrated rate laws can tell us what the concentration will be later in time. Okay, so without getting into a lot of messy details of the derivations, I just wanted to show you the first order rate law. Okay, so first of all, let's look at zero order rate law. Let's look at a zero order reaction. Let's say this reaction starts off at 1 molar, right? And this is a zero order reaction. Now, what does zero order mean, right? Zero order means, right, that this is zero. So if that's zero, then what happens is the reaction rate, right, is equal to a constant. Now, when we do the integrated rate law, the form of the equation actually looks like this. So let me get back to that. So if the reaction rate is a constant, right, that means it never changes, which means the slope never changes. And so that's why this line, right, looks like a straight line. It's a zero order reaction, and the slope, or the which is related to the reaction rate, doesn't change with concentration. So let me explain the equation to you, okay? A sub t, right? This A sub t is the concentration at time t. So t is the time, okay? A is the concentration at that time. Now, A0 is the initial concentration. And so it takes this form of this equation. This is the initial concentration. And I started this graph off at 1 molar, so it'd be easy to look at. And then this, right, is the slope. And this, t is time. This is time. Okay, so now think about it. This is y, right? This is b, and this is m and x. So we're using time as my x-axis, and then we're using at as my y-axis. So if you have a zero order reaction, right, the slope is equal to minus k. That's this part here. if you have a zero order reaction and you want to know the rate constant, you can calculate it simply by measuring the slope of the line. Now, how do you know it's zero order? Because it'll look like this. It'll have no change in slope over time. Okay, so let's look at a first order reaction. So in a first order reaction, what happens is n is equal to 1, right? And this is for a generic reaction A goes to B. Well, the integrated rate law turns out to be a little bit uglier. And if you really want to see how the derivation is done, I actually have it in my typed notes that I posted. You can find those in like a resource in the resources module. There's a page with my typed notes in it. So what does that mean, right? Well, the reaction rate is equal to K times A, right? Well, what happens when A goes down? Well, if A goes down, then the reaction rate goes down. So that means the rate, right, at which the reaction proceeds is getting slower and slower. When you integrate the rate law, it looks like this, right? It's a little bit messy. But we're going to think of this as Y. We're going to think of this as B. And we're going to think of this, let me circle this carefully. This is M, and this is going to be your X. So again, it's this form of Y is equal to MX plus B that we can look at, right? Actually, I'll do this slide in a little bit. So because this equation involves natural logs and people are a little rusty on it, I wanted to go over a little bit of math, okay? Just sort of show you and review with you how you do some of these operations. So I wanted to get this equation into this form, right? So what you need to do is do the following. You need to move the ln of A0, right, over to the left-hand side. That's going to be equal to minus kt. So I subtracted natural log of A0 from both sides. And then what you have to remember when you're dealing with logs is what that is, right? So you go back, some log properties, right? The log or the natural log, the operations yield the same kind of result. If you subtract the natural logs of two numbers, A and B, it's the same as the natural log of A divided by B. So this becomes natural log of A t divided by A0 like this, and that's equal to minus kt. Now this is also a useful equation, but again, I just wanted to show you how that was done. Now, there's another useful equation. This again involves using the log properties, right? Another useful equation is to take the anti-log of both sides. Now remember, there's a log, and every log has its anti-function, right? And in this case, this is a natural log, so the anti-function is e. So we're going to raise e to the power of this, e to the ln at over a0. That's going to be equal to e to the minus kt. Now, what the antifunctions do, right, is they just basically remove what you did in the first function. So in other words, this left side just becomes at over a0. Now, again, I'm trying to show that with this, right? If you have e to the ln of x, it just becomes x, whatever was in there. If you have log of x and you raise 10 to the log of x, so this is the base 10 log, then you'll end up with x. So if you use the anti-function, it just undoes the function. Okay, so in this case, this is going to produce at over a0, and that's going to be equal to, right, e to the minus kt. Now, the form of the equation that people like to have handy is this one. AT is equal to A0 e to the minus kt. Now, what's handy about this equation, right? This is actually the equation that you would use to predict the concentration at some time later. So, to find this, right, to finding AT, you need to know A0, right? We use A0, the initial concentration. We use K, the specific rate constant that we calculated before. And then we just need to plug in the time, the specified time. There's similar equations. Okay, so then back up for a second. And then looking at zero order equations, that's exactly what you would do, right? If you wanted to know what the concentration of A was at some time later, you would plug in A0, you would plug in K, and then the specified time, and that would allow you to calculate AT. Now, the reason why I came back to this example is that this equation eventually will go to zero. And when it goes to zero, it can't go below zero because it represents the concentration of A, and A won't go negative, right? It's an actual concentration. So at that point, on the x-intercept, it just continues on going zero. So this is kind of a different equation than the integrated rate law, okay? But on a first order reaction, it turns out, on a first order reaction, this equation actually never goes to zero. It just sort of asymptotically approaches the x-axis. Okay, so let's take a look at second order reactions. For second order reaction, right, this will be squared, right? So reaction rate is equal to K, for example, times A to the second. That's what the rate law would look like in the rate law. The integrated rate law looks like this. Okay, again, if you want to know how you get to that, you can refer to the notes that I typed out, and it'll have a reference to how you do that. But let's think about just this equation and what it's telling us. This is second order versus first order, right? Let's assume the K's are about the same, right? What happens, right, as the concentration goes down in a second order reaction, the effect is squared. And so because the effect is squared, what does that mean, right? It's going to slow down even faster than a first order reaction. So we expect, actually, when we go to look, and we haven't done it yet sort of intentionally, when we go back and we actually look at first and second order data, what you'll be able to see is that second order reactions on a relative scale slow down faster than first order reactions. What does that mean? The slope changes faster. It gets flatter faster than a first order reaction. Now, I'll show you one other thing. This can also be graphed as a y. This is mx, and this is b. Okay. So this also has the form of a straight line, and this thing that I'm doing by taking a first order and second order reaction and sort of rethinking them as straight lines is called linearization. And we're actually going to use these equations and what they're telling us to do to figure out the rate constants of reactions from graphs. Okay, so this is why the y is equal to mx plus b is important. So let's just do an example. I talked about it in zero and first order. Let's do one for second order. The process is in essence the same for a second order reaction. So we're going to do a second order reaction. It says a second order reaction starts with half molar A. How much A remains after 450 seconds, right? And this is the rate constant. So we'll go back and we'll write the equation. So the equation is this one that we're doing because it's a second order reaction. So this is also an important piece of information. So we're going to write 1 over AT is equal to 1 over A0, right, plus KT. Now, I think I rearranged it from, yeah, I flipped those two. Um, so, let's figure out what our different variables are, right? A0, my initial concentration is 0.500 molarity units, right? Or molarity. And then after 450 seconds, so T is 450, and then K, right, is 4.0 times 10 to the minus third. And this unit here for second order rate constant is basically this. It's 1 over molarity times second, or molarity to the minus 1, second to the minus 1. Typically, you'll see it written like this because this is harder to keep looking nice on paper, for example. Now, we'll plug in the values. 1 over AT equals 1 over A0 plus 400, let's see, 4.0. Sorry, I meant to put molarity down here. 0.500 molar, and then 4.0 times 10 to the minus third, right? 1 over molarity times seconds, and then we're going to multiply that times the time, which would be 450 seconds. One of the sort of places people get caught is by not looking at the units and recognizing that they don't match. And so you have to make sure the units in your rate constant and the units for your time match. If they don't, you need to change the units in your time. That's usually the easiest thing to do. Okay, so this is going to be this is going to become this, 2.00 molarity to the minus 1, right, plus, and then we'll pull out my calculator. I think I could probably do that one without a calculator, but I won't risk it right now. Hang on. There we go. 4 times 10 to the 3, change sign, times 450. That's 1.8. So this whole thing right here is 1.80, 1.80, yeah, 1.8, it's actually 1.8, I'll just mark it there. And the units are, if you think about this canceling, this is 1 over molarity, so this is molarity to the minus 1. So now we can add these two up. They have the same, right, quote unquote, units, and so this will add up to be 3. 3.8 molarity units to the minus 1. Now, this is actually a mistake that a lot of students will do early when they're learning how to do these things, is they'll just say, oh, that's the answer, right? But you notice this is actually 1 over concentration, and this unit on this number is per molarity. So to get to the molarity, then what you have to do is do the inverse of both sides. So let's do that real quick. I'll pull up my calculator. So 3.8, right? And then I have to take the inverse of it like this, and that becomes 263. So 0.26 molar. So make sure, right? Make sure here, don't forget to inverse. 1 over x. Okay, now you don't actually have that problem with zero order and first order, which is why I chose to show the second order, because there's some difficulties just in people getting mixed up in the math, okay? But they're all done basically the same way. You just find your values, you plug them in. Now, let's say I hadn't given you hadn't asked you for the concentration at a time later, but actually gave you that, right? Well, as long as you're given, right? There's 4 different variables here. 3 of the 4, you can calculate the one that's left. So you could calculate a time. You can actually calculate a rate constant this way if you know the order of the reaction, for example. Okay. Okay, so let's look at a first order reaction. I had one in the notes, so I just thought I'd do it. Um, you have a first order reaction. It starts with 1 millimolarity unit, so that's 10 to the minus third molar units of A. How much A remains after 50 seconds, right? And then K is equal to 2.6 times 10 to the minus 2 per second. So these are first order. And actually, you should be able to tell when you study this that, oh, gosh, that unit looks like a first order reaction rate constant because the units are per second for those. And when you do calculations, you'll kind of see in order to get molarities per second, you have to have that in the rate constant. Okay, so we have a first order reaction. It starts with 1 molarity unit of A. How much A remains after 50 seconds, and it gives it rate constant, right? So again, there's different forms of the equation. It's really important that you kind of pick the right one, right? So there's natural log A T equals ln A0 minus KT. There's also AT. Oh, there's yeah, sorry. There's another one. Sorry, still ln AT over A0 is equal to minus KT, and then the other one, still there's yet another, right? Is AT is equal to A0 e to the minus KT, like that. Now, when you do these problems, you'll have all these equations in front of you, right? Make sure you choose the one that is closest to the answer that you want to get, okay? So if you wanted to know, like for example, the rate constant or the time, this one would be the easiest one to use, or this one would be the easiest one to use, because it's easy to isolate that value. On the other hand, if you wanted to know concentration, both of those contain concentration in the natural log, and so you have to do some anti-logs and a lot of other calculations. So the form of the equation people usually choose for this is this one, okay? Because it has concentration at some time later just ready for you to get, right? You just plug values in. So my A0, and it didn't say what units for molarity, so we're just going to leave it as millimolarity units. So 1.00 millimolarity units, and then we're going to have T is equal to 50 seconds, and then K is equal to 2.6 times 10 to the minus 2 per second, right? Now, that could also be written as seconds to minus 1. So we're going to go ahead and we're going to say AT is equal to 1.00, right? And I'll leave the units out here. Well, I'll put them in, I guess. I'll put it in. And then E to the minus, and then 2.6 times 10 to the minus 2 seconds, or per second, right? And then we're going to have T, which is going to be 50 seconds. Again, a common trap for students is not to catch that the units are seconds and then not match them up properly, right? They may not be seconds, right? One might be minutes, one might be seconds. You'd have to do some conversion in there. And then the rest of it's just on the calculator. So we'll pop up the calculator. And we're going to go 2.6, I'll change the sign when I'm all done, times 10 to the 2, negative 2, times 50. So that's 1.3, so I'll change the sign for that. So it's negative 1.3, and then I'll do the E of that. So I'll just go E like this. So it becomes, oh sorry, I think I still have to on this one raise it to a power. So raised to the power, let me double check. E, yeah it is. I thought it was just going to do it for me, but it's not that easy, I guess. That's E raised to the power of, what did I say, negative 1.3, right? So 1.3 0.3, we'll change the sign and we'll hit this, and that becomes 0.275, 0.2725. And my cat is crawling around my desk, so 0.2725, like that. And it doesn't have units because these units will cancel out. So since it's 1 molarity unit, then 1.00 molarity unit times 0.2725 will give me 0.2725, right? Rounded to 3/6, so 0.273 molarity units, like that. And it actually, I did it and had the answer here already. I rounded it, I think, slightly differently. I'm not sure exactly what I did, but it didn't come out exactly the same. That's the answer. Now, it says compare this to the actual data, and you should probably do that. You can actually go back to the first concentration time data in the slides and look to see what it was at 50 seconds. They're not exactly the same because the slopes that I measured, the rate constants I measured, were a little bit different because I used an instantaneous rate and that one used an average rate, okay? But they will be a little different when you do that. Not a big deal, but I wanted to make sure to point that out to you. My crazy cat.